in this chapter 21, we're going to talk about blood. And so in this PowerPoint, we'll talk about just the general components of blood and the functions of those components. We'll talk about the structure and functions of plasma, the formed elements. Then we'll move on to blood typing, hemostasis or blood clotting. We'll talk about some disorders of hemostasis, talk about how blood elements are formed, as well as some different erythrocyte disorders near the end of this lecture. So in terms of blood, you guys, we talk about whole blood as basically just the blood you would extract through venipuncture. And so whole blood has three main components. We got erythrocytes, the buffy coat, and plasma. Now we can separate out these components using a centrifuge. And a centrifuge is basically a device that spins really fast, and it increases the apparent gravity on a sample you put in the centrifuge. Like some of these centrifuges can spin up to like 100,000 times the force of normal gravity. And what this can do then is actually separate out these blood components. It doesn't take that much to separate blood. You only need maybe 1,000 times the force of gravity to separate out these blood components. But these heavier elements like the erythrocytes will sink towards the bottom of the test tube, whereas plasma will float towards the top, and you'll end up with a buffy coat in the center. So the erythrocytes make up about 44% of your blood sample, like an average blood sample. 44% of that blood volume is made up of erythrocytes or red blood cells. And we also call this hematocrit. So when you talk about someone's hematocrit, we're referring to the erythrocytes. The buffy coat is made up of platelets and leukocytes, and you find this in the center of that centrifuged blood. And then plasma takes up the rest of the blood volume, you guys, and that's 55% of your blood's volume. It's mostly water. So your book says a straw-colored liquid. In my eyes, it looks kind of more urine-colored, so sort of like a clearish, yellowish type of solution or fluid. Now, what's important to note to you guys is that all of these components are mixed in whole blood, and they don't separate these components until you centrifuge them. Now, erythrocytes, leukocytes, and platelets are these formed elements. Now, for blood separation, what we see here then is the centrifuge. And so you can take someone's whole blood, put it in a centrifuge, and it'll spin really quickly. Okay, so it spins really fast. What happens then is that the erythrocytes sink towards the bottom of the sample. So you see the erythrocytes here. It takes up about 44% of your blood's volume. Plasma's on top. That's about 55%. And then the buffy coat is about less than 1% or so of your blood's volume. So in plasma, it's mostly water. So by volume, it's mostly water, followed by protein as well as other solutes. So when we talk about blood volume, we also refer to water content. So if you have a lot of water in your blood or less water in your blood, that's going to change the plasma volume, which can also change the proportion of your blood that's the formed elements. So in terms of the proteins you find in plasma, you have albumin, globulins, fibrinogen, as well as other regulatory proteins. And we'll go through the functions of these proteins in a little bit, but it's important to note that plasma isn't just water. It's got a lot of protein in there too. And there's other solutes in plasma too. Electrolytes like sodium, potassium, phosphate, magnesium, other metals. There's nutrients in there, other gases that are dissolved, and waste products. Now, in the buffy coat, you find platelets and leukocytes. Platelets aren't true cells. We call platelets thrombocytes, and that's sort of a misnomer. They're not really true cells because they're just basically a fragment of a cell, but these are necessary for proper blood clotting. And then the leukocytes are also found in the buffy coat, which is sort of a whitish layer here. And the leukocytes include things like neutrophils, lymphocytes, monocytes, eosinophils, and basophils in that abundance. And then the erythrocytes, you guys, are the red blood cells. Now, these red blood cells or erythrocytes, they're also not really a true cell because they lack most organelles and they don't have a nucleus, which means they have difficulty repairing themselves. And so we recycle our erythrocytes about once every 4 months or so they don't last very long. Now, in terms of the functions of blood, we know it's involved with transport. So oxygen, carbon dioxide, nutrients, and wastes are transported by blood. It's involved in regulating things like body temperature, because if there's a tissue that's warmer in your body, like internal organs, blood can pick up that sort of heat and then carry that to other tissues in your body that might be more cool, so it helps distribute temperature around your body. So by having blood flow, it makes your overall body temperature more homogeneous, like less separate, Otherwise, if blood wasn't flowing very well, and let's say if your tissues can stay alive even though blood wasn't flowing very well, you'd have some tissues that would be really hot and other tissues that be really cold, like your skin would be more cold with respect to your internal organs. Blood's also involved with regulating pH levels, so the acidity of your blood and as well as tissues of your body, and fluid levels, because we know that blood can transport fluid, water. So blood can pick up excess fluid from tissues. It can also deliver fluid to tissues. So blood's involved with regulation of fluid levels around your body, as well as protection. We know that blood carries leukocytes, which are basically white blood cells, and they can help guard against infection. Inside of your plasma, you have antibodies, which is the gamma globulin. And these immunoglobulins are involved with immune defense. They can stick onto things that are foreign. And one more thing, you guys, is I'm not sure if it's up here, but blood also protects in the sense that blood protects against too much blood loss, right? Because if you have a ruptured blood vessel, that blood in the local area will coagulate, form a clot, and prevent additional blood loss. So it's involved in protection with that regard. Now, what this table shows then are all the components of blood, as well as the functions of those components. So what this is showing is actually just plasma in particular. So we know that blood plasma is mostly water. And so water is the solvent, or just sort of the thing that helps dissolve a lot of other solutes in that plasma. Second to the watery component of plasma, it's followed by a lot of protein. So the major or most abundant protein you find in blood plasma is albumin. And albumin's a protein that's made by your liver. And one of the major functions of albumin is to exert this osmotic force within your bloodstream. Because what albumin does, it helps attract water and keeps that water in your blood. Because we know that blood has a pressure to it. Due to blood pressure, you can force water out of the blood into your body's tissues. So you'd want to hold on to that water or reabsorb water from tissues back into blood, and that's achieved by albumin. Now, it does play a role with blood's viscosity or stickiness, and it is involved with hormone and some fatty acid transport. But one of albumin's main functions is to retain fluid in your blood because it exerts an osmotic driving force. Now, we'll come back to this in a few chapters when we talk about blood vessels, but for now, just think albumin exerts an osmotic force or water attracting force inside your blood. Now, the globulins are second to the albumins, and these globulins are basically also proteins, but have different functions. So we have alpha, beta, gamma globulins. The alpha globulins are involved with lipid transport and metal ion transport. Beta globulins are involved with iron and lipid transport. And the gamma globulins are antibodies. Now, we've learned in lab, and we'll talk about it again today, that antibodies are immune proteins, and those are basically proteins that can stick onto foreign antigens. So, let's say if you've ever been exposed to like influenza virus, there are antigens on the surface of that influenza virus that you have made antibodies against. That way, if you're ever exposed to influenza virus again, you already have these gamma globulins or specific antibodies against those antigens on influenza virus, and you can attack that virus and help limit the spread of that infection. Another type of protein you also find in plasma is fibrinogen. Remember, fibrinogen is a type of protein that's actually the precursor to the fibrin blood clot, which we'll talk about later. But what happens is this is a soluble protein, so it's normally dissolved in blood plasma. And when your blood clots, fibrinogen can be turned into a protein mesh called fibrin, and that helps your blood coagulate. So we talk about fibrinogen as also being involved with blood coagulation. And again, fibrinogen is made by your liver. Now, last but not least, you guys, we have some regulatory proteins. These are less abundant, but some of the different regulatory proteins can be different enzymes or even protein hormones. So we have enzymes that can degrade hormones. That way they can be removed from your body. Otherwise, there are hormones that are made of protein, like insulin is a protein hormone, or oxytocin is a protein hormone, or vasopressin. Those are all protein hormones you can find dissolved within the plasma of your blood. And other things, you guys, other solutes, so different electrolytes can be dissolved there, nutrients, gases, and wastes. So electrolytes include things like sodium, potassium, calcium, chloride, iron, bicarbonate, hydrogen. All of these carry a charge, like whether it's positive or negative charge. That's why we call them electrolytes, because they can conduct electricity. These are important in your body, and we'll come back to this later. Other nutrients can be carried by your blood too, whether they're amino acids or sugars or cholesterol or vitamins or fatty acids. These are transported around your body through your bloodstream. And other gases too. So we can find that you can find carbon dioxide dissolved in blood, oxygen dissolved in blood, nitrogen, carbon monoxide. There's lots of gases that can be dissolved in blood, but when we talk about some of the major gases that are important in homeostasis, we'll come back to talk about how oxygen and carbon dioxide balance is really important inside your body. Now, wastes are also carried from blood. So we know that wastes are accumulated by your body's tissues, and what helps carry those wastes away from those tissues is blood. So if a tissue is accumulating wastes and it has blood flow through it, the blood can help pick up those wastes and carry that away from the tissue. An example of a waste could be things like lactic acid, which is an acid. You want to remove that from the tissue and carry that away. Or even carbon dioxide is actually a waste that's made by tissues. So CO2 is also transported by your bloodstream. Now, hematocrit is, so all the formed elements here. It can vary with age or gender, but we talked about how hematocrit's about 44 or 45% of your blood volume. So for the hematocrit, we got erythrocytes, leukocytes, and platelets. Now, erythrocytes are the red blood cells. They're pretty small, like 7.5 microns or so. So that would be close to 1/1000th of a millimeter, or meter, sorry. So it's actually pretty small. The functions of erythrocytes are to help transport gases like oxygen and carbon dioxide. They've got a pretty short lifespan. You're talking about 4 months or so. And the proportion of erythrocytes can vary depending on gender, but they remain in a fairly constant range here. Now, leukocytes are the white blood cells, and they're typically larger than the erythrocytes because leukocytes are a true cell. Leukocytes have organelles. So leukocytes have a nucleus. They're going to have other organelles. They also their lifespan can vary in the matter of hours to days to years. Some of the leukocytes can store a memory of infection, so therefore they last years or even decades. Other leukocytes, like the neutrophils, can last hours, like 12 hours or so. So they don't live very long. Now, the last formed element here, guys, is the platelets. And these basically are also not a true cell. They're very small fragments of another cell called a megakaryocyte. These last about a week or so, and they help participate in blood clotting. So on this slide, we're going to look at how to prepare a blood smear. Basically, what you can do is just take a little pinpoint prick of blood. You can use a lance. What you do then is put a little drop of blood on a slide. You can apply a stain, like a right stain. And what this is a nuclear stain. So actually, it's attracted to DNA. And once you apply the stain, you can kind of smear that blood across, put a cover slip on top, and then look at it under a microscope. So this is what red blood cells and leukocytes would look like underneath a microscope once you've done a blood smear. You need to apply a stain, otherwise these cells won't look as distinct or prominent. Without that stain, the cells are going to look more clear. So you got to apply the stain there first. So what we see here, guys, these ones that look more purple, these are the leukocytes, and they actually have nuclei. So the purple stain here is the nucleus. And that's one of the ways we can identify these as leukocytes. And they're larger. Remember, leukocytes are 2 to 3 times larger. Whereas these red blood cells, they even look kind of red, but there's no nucleus, like there's no purple area. In fact, they almost look like they have a clear center. Now, it's not as though these cells are hollow. It's just that the center of a red blood cell is thinner than the peripheral edges, so it's easier for light to pass through. Okay? And that makes sense. Now, if you guys look really closely, there's sort of like these little dots on the slide here. And these little tiny dots are the blood platelets. It almost looks like dirt on the slide. But those tiny little dots there are the blood platelets. So here's some platelets. And again, they're really small because all they are fragments of cells, not even entire cells. So if we zoom in on this, you can see this better. So here are the leukocytes, or white blood cells, and there's different varieties of these. We can tell because they're nucleated, so they're white blood cells. All of these are the red blood cells, you guys, and they don't have nuclei, so the centers look more clear. Again, the structure of a red blood cell is a biconcave disc, so the center is thinner, and therefore it looks more clear under a microscope. And then all of this sort of things, the stuff that looks like dirt off the side, those are platelets. So you can identify platelets here. Now, in terms of erythrocytes, you guys, again, they're not true red blood cells because they lack a nucleus or organelles. They have this biconcave shape, but they can also, due to this biconcave shape, it makes them more bendable, more flexible. Because some of your smallest blood vessels are only wide enough to fit one red blood cell through. Okay. Now they can actually line up in this little pattern called rouleau, which is like stacked coins. If that makes sense. And by having this biconcave disc shape, they're more bendable, more flexible. But it also gives them more surface area for gas exchange. So on this slide, what we're looking at then is the biconcave disc shape of those red blood cells. You can see it, the cutaway version here. So it almost looks like a donut, but the center here isn't completely through. By having this particular shape, it turns out there's a lot more surface area of plasma membrane on a biconcave disc than if you had like a sphere of a cell. So you can fit more plasma membrane here by having this shape, which means that this is better at gas exchange. Like if there's more area for gases to move across the plasma membrane into or out of this red blood cell. Now on the inside of the red blood cell, remember it lacks organelles and a nucleus, and so it's really all just full of hemoglobin. So hemoglobin's a specialized protein that's involved with gas transport, and every red blood cell here is full of about 250 million molecules or so of hemoglobin. Each of those hemoglobin molecules can carry 4 oxygen molecules. So every single red blood cell could potentially carry up to 1 billion oxygen molecules. That's just one red blood cell. But you're going to have millions of these things in every unit of blood. So it means your blood can carry a tremendous amount of gas. So if you look at red blood cells under a microscope here, they can kind of line up. And this is that rouleau pattern. So this is actually one of the smallest blood vessels in your body called a capillary. And you can see here that the capillaries are just barely wide enough to fit one red blood cell through. In fact, some of your smaller capillaries are even so small that red blood cells have to squeeze through. And by having that biconcave disc shape, they can bend. They're more flexible, and they can squeeze through some of your smaller vessels. If someone has a disease that affects the shape of the red blood cells, it can make them less bendable, less flexible, and therefore they could be more prone to forming blood clots. Or it could make the red blood cell weaker and more likely to tear open, rip apart, and therefore be no longer functional, if that makes sense. So we'll talk about some examples of those later. But let's first talk about the structure of hemoglobin. So every erythrocyte or red blood cell contains about 280 or 250 million molecules of these. Every hemoglobin molecule consists of 4 separate protein molecules. So we have 2 alpha chains and 2 beta chains. And those 4 separate proteins all clump together to form one hemoglobin molecule. So if we look at this, you can see this here, the alpha chains and the beta chains. Now at the center of each at the center of each globin chain, you find a heme group. So there's one heme group in this center of this alpha chain. There's a heme group in the center of this alpha chain. And looking at this heme, this was zoomed in over here, it's a kind of a more complex organic compound. But what's important to note is that there's a central iron atom. And it's the iron here in the heme group that's involved with binding to gases like oxygen and carbon dioxide. Okay, so this is the sort of the central component to gas transport. So if someone doesn't have enough iron in their diet, or if they have a disease of iron absorption or improper iron transport, what you'll find then is that they could have iron deficiency anemia, where they don't have enough iron available to make a sufficient amount of hemoglobin to appropriately transport gases in their blood. Yeah. And so anemia is actually one of the most common diseases worldwide because of limited iron availability. But each of these hemoglobin molecules is a central iron atom, which is involved with the gas transport. So it helps bind to carbon dioxide, oxygen, and carbon monoxide. So that's that heme group, you guys, contains a central iron atom here. And because every iron atom can bind with an oxygen molecule, and every hemoglobin molecule has 4 heme groups, each having an iron, that means every hemoglobin molecule can carry up to 4 oxygen molecules. And we'll come back to this in 2 weeks when we talk about gas transport throughout your body with the cardiovascular system. Now, what this slide is showing is how red blood cells are recycled. Remember, we talked about how red blood cells only have a lifespan of about 120 days or so. Okay, so their lifespan is fairly short in terms of your whole lifespan, so 4 months or so of a typical red blood cell. You might wonder, well, why do red blood cells have such a short lifespan? What do you guys think? Yeah, there's no nucleus to make new protein, and they don't have organelles to fix the cell. So basically, these cells have they're like kind of a one-shot thing, right? Once they get damaged, they can't really repair themselves very well. There could be some enzymes that might repair some substances, but more severe damage isn't repairable. So these red blood cells have a particular shelf life, a lifespan, and in your blood, that's 120 days or so on average. Now, these are actually recycled by your spleen, liver, and red bone marrow. So what happens is that one of the functions of the spleen is to monitor the blood cells that pass through your spleen. And if one of those red blood cells is damaged, there are specialized cells inside the spleen, like Kupffer cells, that will engulf that damaged red blood cell and then break it down. Okay? Now the components of that red blood cell then are recycled. And so the protein and the iron you find in red blood cells is recycled by the spleen. So it's actually used again by other cells of your body. The liver actually has the same function. This is one of the reasons why you can live without a spleen. So if you get a splenectomy, it's not as though you can't break down any red blood cells anymore, because your liver can carry on that same function. So the liver actually also can help recycle damaged red blood cells. So what can happen then is that the liver and spleen will break down hemoglobin into heme. Now, the iron can be used and stored by either the liver and spleen or other parts of your body. And then heme here is converted to biliverdin, which is converted to bilirubin, and bilirubin is green. So this is one of the reasons why if someone gets a lot of red blood cell breakdown in their body, and that bilirubin's not eliminated from their body, that's why you can get jaundice, or sort of a yellowing of the skin, because now the bilirubin is accumulating in their body's tissues rather than being excreted by the liver. You might wonder, well, what does the liver do with that bilirubin then? It puts it in bile. And that's one of the reasons why bile is green, is that it's full of bilirubin, which is made from biliverdin, which is the breakdown product of heme and hemoglobin. So our body actually recycles this in the process of digestion. Now, in several weeks when we come back to digestion, we'll talk about the importance of bile in digestion as well. So it's weird that some of the components of your dead red blood cells are used to digest things that you ingest, which is weird. You have a question?
Yeah, the book said that biliverdin is green and bilirubin is yellow.
Well, like greenish yellow.
Okay.
Yeah, exactly. Now, what's interesting too, you guys, is that this bilirubin can be broken down further by bacteria in your gut into something called stercobilin, which is brown. And this is one of the reasons why feces are brown, because it's broken down bilirubin and it's converted by bacteria. That's what makes poop brown. So it's one of those things like, kids ask these questions that are so simple but also have usually complex answers. Yeah, like, why is poop brown? It's like, oh wow. Okay, well, why is it that if I eat a lot of red hot Cheetos, why is my poop still brown, right? Why is it not red? Well, in part it's because of the stercobilin. That's the breakdown product of hemoglobin. So it's actually kind of cool. Now, what's interesting, guys, is these components can be reused again by your red bone marrow to make new red blood cells. So it's kind of interesting. That whole process takes about 120 days or so. And even your red bone marrow can break down damaged red blood cells. I know it's not on the slide, but red bone marrow itself can also help degrade old and damaged red blood cells. Now, what we're going to do next, you guys, is move on to talk about blood types. So although red blood cells don't have organelles, they still have what we call surface antigens. And surface antigens are basically molecules that could potentially stimulate an immune response. I like to talk about these surface antigens as almost being like gang signs, right? Like every cell in your body is kind of throwing up a gang sign, and that gang sign says, hey, I'm part of this cell, like west side, right? And so I belong in the west side, right? So what are these surface antigens? We got A, B, and RH, okay? Now these are basically glycoproteins that are unique to you. Now you can have other people out there that have similar blood type, but based on your genetics, you will make a specific type of red blood cell with a specific glycoprotein surface antigen or gang sign, right? So based on your inheritance from your parents, like your red blood cells will be throwing up their own gang sign, right? Whether it's A, B, or RH, or a mixture of any of those three. Yeah.
So if somebody has the same blood type as me, though, they're going to throw up the same gang sign.
You got it.
So it's not the same.
Yeah. So if someone else has the same blood type as you, they're throwing up the same gang signs. You got it. So we'll come back to that.
So they're like from the west side in like California.
Yeah. Right. All right. Now, those are the surface antigens, you guys. So if someone has the A surface antigen on their red blood cell, what's their blood type? A, right? What if they have A and B on the surface of the red blood cell? AB. Now there's a third one here, and I don't think it's on the slide yet, but it's called RH factor, or Rhesus factor, and it's another type of surface antigen that's important to talk about because it could potentially stimulate an immune response. You might wonder, what's the point? Why have any cell in your body like throwing up gang signs, right? Like why even have these glycoproteins? Well, they're parts of your immune system where your immune cells can determine self from non-self. If your immune system knows to recognize that red blood cells should normally have A antigen, then they're not going to attack that red blood cell. But what if your immune system encounters a surface antigen that shouldn't be there? Like if you have A blood type, but then you're exposed to blood cells that have B surface antigen on them, that's considered foreign, so then your immune system will attack those red blood cells, right? So that would be an improper transfusion. So, and we'll talk about that later. Now, what's also important to you guys is that your immune system will make what we call antibodies or gamma globulins against surface antigens that you don't find inside your blood. So this is under normal conditions. So if you have A blood type, your immune system would not make anti-A antibodies because that wouldn't make sense. You wouldn't want your immune system to attack your own blood. If you have AB blood type, you wouldn't make anti-A or anti-B antibodies. Again, that wouldn't make sense because then you'd also be attacking your own blood. So what antibodies do they make then? Well, if you have the A blood type, but B is not normally found in your blood, then B antigen would be considered foreign, right? Which means that your immune system could make anti-B antibodies. And you can find these inside your bloodstream. Yes?
Does that protect us from some blood-borne pathogens like hepatitis C or HIV since it's attacking the...
Sometimes these antibodies can attach to multiple antigens, and but typically they're specific. So it's unlikely that like hepatitis, and I think A and B has nothing to do with this, but it's unlikely that hepatitis would have the same surface antigens as what your body could make, although that is possible. That can happen. And so what's weird, and we'll talk about this later in pathophysiology, is that some people who are exposed to infectious agent, the antigens on that infectious agent might be different, but also similar enough to your own body's antigens. So if your immune system starts to attack that foreign invader, it might also start to attack itself. So there are some forms of autoimmune disease that occur in response to an infection. So once you're infected with this organism, like that could actually cause autoimmunity because then your immune system is sort of inappropriately targeting yourself because your own self antigens might be similar enough to those foreign invader antigens. So it's interesting. Yeah. But typically antibodies are more specific. So very specific. Now, what happens to you guys is that if you encounter any blood that it shouldn't belong in your body, and let's say that there are surface antigens on that foreign blood that you don't normally find inside your bloodstream, what can happen then is that you can get an agglutination reaction. And agglutination just means clumping. So this is basically where antibodies will attach to the surface antigens of that foreign cell, causing those foreign cells to clump together. And that can lead to things like blood clots. It can cause these cells to rupture open and spill a tremendous amount of hemoglobin into your bloodstream. And both of those are not good. And we'll talk about the signs and symptoms of transfusion reactions later. So what this slide has shown you guys is different blood types. You have type A, B, AB, and O. O isn't a specific antigen. O just means the lack of A or B. So we call type O, just they don't have A or B. There is no O antigen. It just means that there's no A or B present there. Okay? So if someone had type A blood, what this means is their surface of their red blood cells would be covered with A antigen, right? Now, would their immune system make anti-A antibodies? Would that make sense? No, because then those antibodies would attack their own red blood cells. However, in someone who's type A, they will make anti-B antibodies because then those can attack B antigens because those are considered foreign. How about with type B blood, you guys? What surface antigen would you find on the red blood cells? B? And then what antibodies could that person make? Anti-A antibodies because A is considered foreign. How about type AB blood?
They don't have any antibodies.
So they have A and B surface antigens, and you wouldn't want to make anti-A or anti-B antibodies because those would attack those surface antigens on your cells. And then how about someone who has type O blood?
No antigens.
They don't have A or B antigen, right? And it's not to say that they have no antigens at all. It just means they don't have A or B. Now, there are more than 20 different types of surface antigens, but we just talk about A, B, and Rh because those are the ones that are very immunogenic, and they're more likely to cause very severe immune reactions. But what's interesting, and our book doesn't talk about this, but it's something to consider, is even if someone has the same blood type, like A, B positive, let's say that, they both have A, they could have different surface antigens other than A, B, and Rh. That could be different enough where you can still get a transfusion reaction, even if their blood type's the same. But it's less likely to occur if they share the same A, B, and Rh antigens. But there are other different types of surface antigens. Like there are more than 20 different types. And so that's something to consider. We only talk about A, B, and Rh because those are the big ones. They're most likely to cause an immune reaction. But there are other varieties. So cross-matching is a little bit more complicated than what we're going to talk about today. But this is sort of the basis. This is the basics. Now, the Rh blood groups, you guys, refers to this D surface antigen. So Rh means Rhesus Factor. And the reason being is that rhesus monkeys also make this. So you'd find Rh factor on the surface of rhesus monkey red blood cells as well. And so if you're Rh positive, that would give you the positive symbol next to your blood type, and that means you have D surface antigen, or Rh, on your surface of your red blood cells. If you have negative on your blood type, that means that you don't have Rh. So that's what we say, just no D surface antigen. So just D is another way to talk about Rh factor. Okay. Now, for an individual who's Rh positive, would they make anti-D antibodies? No, it wouldn't make sense because then you'd be attacking your own red blood cells, right? Now, for a person who's Rh negative, could they make anti-D antibodies? Yes, but they have to be exposed to that blood multiple times before they start making enough antibodies to really get a reaction. Okay, so just something to keep in mind. Now, these agglutination reactions occur during, let's say a mismatch, like an improper blood transfusion. So the example here is that we have type A donor blood, okay? And this is given to someone who also has type B. I'm sorry, take that back. We have a donor with type A blood and a recipient with type A blood. So if the donor has type A blood and the recipient has type A blood, is there anything that the recipient could attack and consider foreign in this example?
No.
RH isn't discussed here, so we'll keep it simple, A and B. Then no, so that we don't see a clumping reaction, right? Which means that is a potential good match. So this is what we're talking about, like a transfusion reaction. You mix their blood and you see if there's a reaction. If it doesn't clump, they could be a good match. What if we had someone who's a donor that is type A blood type, and then you have a recipient with type B blood? What antibodies will the person with type B make? Exactly. So if you have a type B blood type recipient, they're going to make anti-A antibodies, which means that if they receive type A blood from a donor, you're going to get a transfusion reaction where the recipient's anti-A antibodies will attach to the A antigens on that blood of the donor, and that causes a clumping reaction. So this would indicate that this is not a good transfusion right there. Because this clumping, you guys, I know it doesn't sound like it's very dramatic, but that clumping can cause blood clots that can clog your blood vessels. And it can also stimulate such strong immune responses that can put you into shock, which is where basically your blood pressure drops out and you can't supply your body's tissues with enough oxygen and nutrients to meet their needs. So that's why it's so important to make sure that these things match up well. Now, transfusion reactions, you guys, occur if there's mismatched blood. It's basically where the donor cells attack the recipient's plasma agglutinins. And these agglutinins can clog small vessels. It can also cause red blood cells to rupture and release hemoglobin in the bloodstream. The reason why you don't want hemoglobin in your bloodstream is that all this protein now in the blood can clog the filtering mechanisms of your kidneys. Your kidneys are basically big organ filters. And if you get a tremendous amount of protein in your bloodstream due to red blood cells tearing open, then that can clog your kidneys and lead to irreversible kidney damage or even kidney failure. Now, this can result in diminished oxygen carrying capacity because of loss of hemoglobin, less blood flow if vessels are blocked by those agglutination reactions, and hemoglobin in the kidney tubules, which can lead to renal failure.